Hi everyone, welcome back to Math 256. This is Scott. Let's get started. Now we're going to talk about section 3.2, where we will look at the general solutions to linear differential equations. This is 3.2. General solutions. To linear differential equations. And here what's special now is that we're going to be talking about linear differential equations of any order. So here's our setup. A linear differential equation of order n. So what that means is we have derivatives up to the nth derivative of y. So we can say the nth derivative, and then we've also got all the derivatives on down to the 0th derivative, and there are functions such as p1 of x n minus 1 plus until we get down to the nth term in this sequence. I guess I should say the n plus first term of the sequence, but it's going to be Pn of x times y and the 0th derivative, so that's just y itself, and then that equals just some other function f of x. Now to start with, we're going to look at a special case where this is homogeneous, and that means f of x equals 0. So a special case, homogeneous equations. And those will have the form just like what we just wrote. However, the f of x is just going to be identically 0. Okay, so now in this special case, what we're going to look at is the nature of the solutions that they can have. So here's a note. A degree n linear, I should say linear homogeneous differential equation can have at most n linearly independent solutions. So what this means is that if we had more than n linear solutions, one of them would have to be expressible in terms of the others. Furthermore, though, actually, if we have any n linearly independent solutions. So if we have n linearly independent solutions, then any other solution can be expressed as a linear combination of them. So what this means, if we're talking linear algebra terms, is the following. So thus, the dimension of the vector space of solutions to a degree, I should say to an order n, same thing, to an order n homogeneous linear differential equation is n. So the dimension of the vector space of solutions to an order n homogeneous linear differential equation is n, is whatever the order is. Now, what does it mean specifically for n functions to be linearly independent of each other? So, linear dependence for n functions. So what it means for n functions to be first linearly dependent. So n functions are linearly dependent if any non-trivial linear combination of them is identically zero. In particular, C1 f1 of x plus C2 f2 of x up to the last one, Cn fn of x is identically equal to 0 with C1 dot 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 up to the last one, Cn, not all 0. And then they are otherwise said to be linearly independent. Now there's a test for linear dependence of functions. We're not going to make explicit use of it very often. We'll more or less actually just rely on our intuition more than anything else for determining whether functions are linearly independent of each other. But there is a test. It's called the Wronskian determinant for linear independence. So we're not going to, as I said, make much use of this because it's a little bit more trouble than it's worth for us. So this is a test for linear, you could say independence or dependence. And it's equal to the determinant of f1, f2, up to fn, followed by the first derivatives of those same functions, f1 prime, f2 prime, to fn prime, and then these continue down until you get down to the nth derivative. So it has to be a square matrix, otherwise the determinant is not defined. So the nth derivative of f1, the nth derivative of f2, and then going down here, we're going to have the nth derivative of fn. So it's the determinant of all these, and it's the determinant calculated in the usual linear algebra way. And what the Wronskian will tell you is whether the functions are linearly independent of each other, and you can determine that by whether the Wronskian is identically zero or not. So the f1 to fn are linearly dependent if w is identically zero and independent otherwise. When necessary, the Wronskian will be what we'll use to prove that a collection of functions is linearly independent. But it's not a convenient way of checking whether something is convenient, it's only a convenient way of proving it. So, let's now move on and talk about some other important facts about these linear differential equations. And we'll go in parallel to some of the things that we established in the last section. So first off, there's the principle of superposition. So this is, again, just like last section, this is of homogeneous. Homogeneous linear differential equations. And basically what this means is any linear combination of solutions to a linear homogeneous differential equation will be another solution to that equation. So in other words, the solutions to the homogeneous linear differential equations of order n are in fact the vector space that we previously hinted that they would be. Now also, there is the existence and uniqueness. Uniqueness theorem. Now, at this point, we don't need it to be homogeneous anymore. So this is including non-homogeneous. differential equations, still linear for now, but not necessarily homogeneous. So here's the setup. We have an interval, an open interval I, and it includes the point x equals a. Now p1 of x up to pn of x and f of x are all continuous. On that interval. So that's the setup. Then, for any initial conditions y of a equals b naught, y prime of a equals b1, up to finally yn of a equals bn, the linear differential equation yn plus p1 yn minus 1 plus dot 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 up to pn y equals f has a unique solution on I. So as long as the functions that make up the differential equation are continuous, there will be a solution, and it will be unique. Now we can actually go a little bit further in breaking down the solutions to these differential equations based on the principle of superposition and the fact that that this particular equation is related to a homogeneous equation. So here's a note. So if we have a non-homogeneous differential equation, we call the associated homogeneous differential equation the one that we get by just setting the non-y side to 0. Note: given any non-homogeneous equation, by which I mean differential equation, yn plus p1 yn minus 1 up to pn y equals f, we call the equation yn, so basically same functions, except that where there was an f, there shall now be a 0, p1 yn minus 1 up to pn y equals 0, the associated homogeneous equation. we call the general solution and that includes with constants, let's say with unknown constants, included. We call the general solution with unknown constants included to the associated homogeneous equation the complementary solution. And we write YC. And then we can write any solution to the differential equation y n plus p1 y n minus 1 up to p n y equals f in the form y equals yc plus yp, where yp is any particular solution to the original non-homogeneous equation. And then our goal in this is going to be, so this is going to be a particular solution, and this one has no unknown constants. No unknown constants for yp. And then our goal is going to be to figure out what the unknown constants have to be in YC to match any given collection of initial conditions. So then our goal will be given initial conditions find the values of what used to be unknown constants in YC to get a specific solution to an IVP. So in the first installment of this, we are going to be given the YCs and the YPs, and gradually as we build up our skills, we'll be able to find them ourselves. So the first category of these problems is going to be given the YC and the YP. We're going to have just pin down the constants. So the first category, which is all we're going to do in this section, will be given YC and YP, and given YC and YP, and an initial condition set, really. If it's order n, you'll need n initial conditions. We'll find the values of the constants, which we'll always call C1, C2, etc. And as an example, let's take something like this. So here's the differential equation, y double prime minus 2y prime plus 2y is equal to 2x. We'll be given furthermore some initial conditions. Y0, we will be told, is equal to 4. Y prime of 0, we will be told, is equal to 8. Now, it would be, from last section, within our ability to find actually the complementary solution here, the solution to the homogeneous equation we'd get if that were 0. That would be within our grasp because it's only order 2 and we know what we have to do. We would not, however, be in a position to say anything about YP at this point. But right now, we're going to set our sights low and we're just going to be given the complementary solution and the particular solution that we're going to be using. And then it'll be up to us to specify the missing pieces here. So the complementary solution is going to be e to the x times c1 cosine x plus c2 sine x and this is because what we would end up with here is a characteristic equation with complex solutions. So that's what leads to a cosine and sine based solution. And then we will also be told here, we'll figure out later how to find these things, but we'll be told for now a particular solution, of x plus 1. So it's x plus 1. Okay, so that's yp equals x plus 1. I didn't make any change, I just rewrote it. Got a little cluttered there. So we're just gonna. Now this is going to be the general format of the solutions here. We know that every solution is going to be made of a combination of these, but what we are missing here is the particular values of the C1 and C2. And we need to use the initial conditions to find those. Now, in order to use the initial conditions to find those, we are going to need to be able to take the derivative of this, and to do that, it'll be easier if we distribute the e to the x in. So c1 e to the x cosine x plus c2 e to the x sine x plus x plus 1. Now, again, we're taking on faith that this actually is a solution to this. We'll learn in a later section what's called the method of undetermined coefficients, which will enable us to actually find these particular solutions for ourselves. But for now, we have to take their word for it. So, now we would need to take the derivative in order to be able to plug in the second initial condition. This would be enough to plug in the first initial condition, but one equation is not sufficient to find the values of two unknowns. So that means we're going to need to be able to use the second one, so we're going to need the derivative. It's going to be c1 times, and here, if I take the derivative of this, it'll be the product rule, so that's going to be e to the x cosine x. And then we're going to be leaving the first alone, taking the derivative of the second, so it's going to be minus e to the x sine x. And then for the c2, it's going to be very similar, e to the x sine x. And then take the derivative of the second, leaves the first alone, so it's going to be plus e to the x cosine x. Plus x plus 1. Okay, so now I plug in the initial conditions in order to find the missing values of the C1 and the C2. So y of 0, we are told, is equal to 4. And that means that 4 is going to equal, plugging in 0 here, I can do it in any form of the equation as given. But the important thing about this is it's going to be C1, and cosine will equal 1 when you plug in 0. Sine will equal 0 when you plug in 0. So it's going to be C1 plus, and then by my reckoning here, we're just going to end up with a 1 is the only surviving term. So that gives us C1 is equal to 3. Conversely, y prime of 0 equals 8. So that's going to give us 8 equals, and now plugging it into all the pieces that will not go to 0, or so I'll have C1 times, looks like it's going to be 1, plus C2 times, looks like it's again going to be 1, plus 1, just the second initial condition, plugged into the y prime. C1 we've already actually found is equal to 3, so that's going to be 8 equals 3 plus 1 is 4 plus C2, which means that C2 must equal 4. And then finally, that means that the overall solution here is what we get when we put those together. So y is going to equal e to the x times 3, that's C1 cosine x, plus 4 times sine x plus x plus 1. So that's now going to be our overall solution to this particular initial value problem, incorporating now the two values that we had for the C1 and the C2. Okay, so that's what we can do if we are told in advance the complementary solution and the particular solution. However, that won't always be the case, and so in the next section we'll learn what to do if we are not given those things. Alright, until then, bye.